Okay, let's get started. Welcome, everyone. My name is Kevin Lynch, and I'm the editor-in-chief of the IEEE Transactions on Robotics and director of the Center for Robotics and Biosystems at Northwestern University. It's my pleasure to introduce today's panel, the second in a series in the Grand Challenge of Robotic Dexterity. The purpose of this series is to bring together thought leaders in robotic manipulation and to engage the broader community on topics such as the challenges to achieving advanced dexterity, high impact applications of robotic dexterity, and the potential economic and social impact of easier to program, more dexterous robots. This series is motivated by the recognition that progress in robotic dexterity has been slow, but also by the belief that the convergence of emerging technologies and the increasing interest in manipulation will lead to a rapid increase in capability. Today's panel is on novel materials for robust grasping and manipulation, and my main job is to introduce the moderator of the panel, Carmel Majidi. Before I do that, however, I want to plug the next panel in the series on the economics and societal impacts of the coming dexterity revolution, moderated by Julie Shaw of MIT, which will be held on March 1 at 1 p.m. Eastern, noon Central. More information on the panel is forthcoming. All panels are being recorded and will be available for viewing after the event. This panel will run for about 40 minutes, followed by questions from the audience. You can submit your questions at any time using Zoom's Q&A function. Now it is my pleasure to introduce our moderator, Carmel Majidi. Carmel is the Clarence Adamson Professor of Mechanical Engineering at Carnegie Mellon University. His research focuses on novel materials and hardware architectures for creating soft machines and robots that mimic the mechanics of natural biological tissue. His journey to soft robotics began with a fascination for how natural organisms, from insects to wall-climbing lizards, could inspire the next generation of machines. Early in his research, Carmel found that novel materials were a key element for creating robotic systems that matched the rich versatility and multifunctionality of animals and insects. As head of the Soft Machines Lab at Carnegie Mellon, Carmel has continued his work on expanding the palette of materials used to create machines and robotic systems with a special emphasis on soft matter. This includes elastomers and gels, liquid crystal elastomers, liquid metals, and other types of materials and fluids. Recently, his interest in soft matter has been directed towards challenges in robot grasping. Novel materials have the potential to make robot grippers more capable of handling fragile objects, more robust to misalignments and disturbances, and universal in their ability to grasp objects with a wide range of shapes and materials. However, there are a number of challenges to practical applications. To explore these challenges, Carmel has invited experts from a variety of disciplines. I'll now pass it on to Carmel, who will say a little bit more about this exciting new direction in robot grasping and introduce the panelists.
Thanks, Kevin, for the introduction. It's a great pleasure to be here and serve as moderator for this second webinar on grand challenges on robot dexterity. So for this session, we'll be talking about the role of novel materials in robot gripping and manipulation. And I think we all have a picture in our head of a robot arm or end effector doing pick and place operations or assembly tasks, say in a manufacturing plant. These robots typically use jaws, parallel plate grippers, suction cups to lift and manipulate objects, and are precisely engineered and controlled for performing repetitive industrial tasks. But what happens when we take these robot arms outside of the factory setting and move them into our homes, hospitals, and businesses? Are the hardware architectures that are so ubiquitous in industrial automation well suited for performing non-repetitive tasks with a wide diversity of objects? Do we need to think beyond existing gripper designs and explore other types of materials and mechanisms? Are anthropomorphic dexterous hands the answer? And do we need to start utilizing methods in soft robotics for compliance, actuation, and sensing? Today in this panel, we'll hear from technical and thought leaders as they share their views on the state of the art and key bottlenecks in addressing these challenges. In particular, we'll examine the challenge of robot dexterity from the perspective of novel materials and explore ways that they can be used to create robot end effectors that are more versatile and robust for use in everyday settings. During the second half of our discussion, we've reserved time to take your questions. We've already had some questions during the sign-on, and the Q&A function is going to be open through Zoom. So feel free at any time to enter your questions. Kevin is going to be moderating the Q&A board throughout the session, and he'll just pass those along to me as I moderate. All right, so let's introduce our panelists here. So we have Elliot Hawks. He's an associate professor in the Department of Mechanical Engineering at UC Santa Barbara. Elliot's research focus is on bringing together design, mechanics, and non-traditional materials to advance the vision of robust, adaptable, human-safe robots that can thrive in the uncertain, unstructured world. Current projects include bio-inspired microstructured adhesive materials, nonlinear compliant mechanisms, high-power soft actuators, soft exoskeletons, and growing robots. Next, we have Tess Hellebrekers. She's a research scientist at Meta AI. Her research focuses on developing soft and stretchable sensors for robot applications. This includes sensing skins for hybrid robots. So these are conventional robots with compliant surfaces. She also works on fully soft robots, or in other words, robots made of completely compliant materials. Her interests and current efforts are also directed towards investigating soft sensor integration and the corresponding systems engineering challenges. On the panel, we also have Nancy Pollard. She's professor in the Robotics Institute and Department of Computer Science at Carnegie Mellon. Her research combines robotics and computer graphics and the use of motion capture to guide robot motion and grasping, and the use of robotics to synthesize the motion of people in computer animation, with a particular focus on the motion of the human hand. She also has applied her expertise to develop several soft manipulators for handling plants as part of the CMU AI Institute for Resilient Agriculture. And last but not least on the panel, we have Jan Visell. He's an associate professor in the Department of Mechanical Engineering and Biological Engineering at UC Santa Barbara. He directs the Retouch Lab, which pursues fundamental and applied research on haptics, robotics, acoustics, and emerging materials technologies. This includes exploring emerging opportunities in high-fidelity haptic display for interaction in virtual reality, soft material robotics, and contributions of interfacial continuum and fluid mechanics to the domain of human touch perception. Right, so maybe just to help us get to know the panelists just a little bit better, I'll just start with a few opening questions. So Elliot, I'll start with you. So Elliot, you've looked quite a bit at how natural organisms like the gecko lizard control their surface interactions. Are there lessons from nature that can inform how we could design robot end effectors better suited for certain challenging tasks?
Yeah, absolutely. So let me just show a couple of slides here to help you guys get to know me and my work a little bit. So this is StickyBot, and StickyBot is inspired by geckos and their ability to grasp surfaces, and this is where my work began. And here's another version, a little smaller, a little stronger. This is pulling my computer up the wall. But what we realized was that these materials were able to grip in a way that's not normally used in robotic gripping. And so this is a close-up of the gecko-inspired material, where it's this very fine hair-like structure that this is about 100 microns long, touches the surface, and when you apply a shear load, it grips the surface. And so what's neat about it is that it's different than traditional friction that we're used to using when we do grasping, or most robotic grippers do. So this is a friction cone here. So we have the normal force, which is down, and then the shear force, which is the side. And a friction cone, basically, as you move around like this, you won't slip, and then you go too far, it'll slip out to the side. But in contrast, you can have a sticky material. This is something that goes below the axis in the normal force. So if you pushed it down, it would actually stick. And the cool thing about the gecko adhesive is it looks like this. And so what so here what's going on is basically as you apply more shear force side to side, you get adhesion, so below the x-axis. And what we realized is from the climbing robots that we saw this behavior and we thought, well, what could this mean for grasping? And so I think, Carmel, this is an interesting material that could enable new types of grasping, right? And so that's why we got excited by it. And just here's some examples of it in action. And so it's just a film of it. You can set it on a material, and then when you pull that shear force, it grips. And when you release it, it falls off like that. I'll move on now. I have lots of videos of this thing picking lots of things up, but we'll probably have lots of those for today later on. So maybe I'll stop there. But the key takeaway was that, you know, with a new material, kind of the forces enabled in the grasp became different, and that meant we could do things like pick stuff up without really squeezing it, which is kind of cool.
Excellent. Thanks, Elliot. All right, so Tess, so as someone who's been working at the intersection of AI and novel materials for robotics, what do you see as the connection between materials and some of the data-driven techniques that you've been using?
Yeah, absolutely. Thanks for the intro, Carmel. I hope you can see my screen. I also prepared just a few slides and some videos. Like Carmel said, I'm working in soft sensing, but in the last couple of years, I've been really narrowing down on magnetic soft sensing. So some of my most recent work we called reskin, and it works by letting a deformation of magnetic particles create a really unique magnetic flux field. And this also led me into like the data-driven side of things, because there is no closed form solution for this kind of sensing. So we're really interested to see like how we can collect this kind of magnetic tactile feedback in robotics, wearables, kind of unstructured environments, and then using data-driven methods to help us start making sense of it. So like ultimately my goal is to make sure we have a interpretable, understandable output from these raw sensor signals. And some of my like favorite work happens like in a very unstructured way. So we know that we can put these compliant materials on tons of surfaces. And then my next step is really to figure out how we can interpret all of that data into hopefully something useful for our communities.
Great, thanks, Tess. Yeah, in our discussions, it's going to be very interesting to kind of share different perspectives on kind of the role of sensing, with these soft material systems. So thanks for sharing that. All right, Nancy. So I mean, you've been working on a series of various soft hand designs, and these are not just for grasping, but also for manipulation. So I'm kind of curious about what from your perspective, what you found is kind of easy, hard with manipulation with these soft hands.
Sure. So thanks, Carmel, both for the introduction and the great question. I think in terms of what we saw to be easy, with our first generation of hands, which is shown here, they were made of expanding foam and based on a mold system. So they were fully solid, soft materials. And what we found to be easy with them, surprisingly easy, was to create robust in-hand manipulations. So I'll show you a little bit of that. But first of all, it's not just being able to create the manipulations, but we could change the design of the bodies. We could change their rest shape. We could change the tendon layout, make it more human-like than some of the standard robotic designs. Those are the same stuff that might be in your couch, for example. Then we put a glove on it and sew tendons through that glove. And I think what we found to be really helpful here is just the inherent compliance made it easy to create these grasps, create the manipulations that you see here. We didn't have to worry about fingers colliding, anything breaking. Interactions with the environment became quite a bit more robust and secure. And following that, we moved on to trying to systematize that a little bit, try to think about benchmarking it. This is work with, of course, with Carmel and one of his students. So you'll know that one well. And then we went on to moving in a little bit different direction with thinking about a more rapid design pipeline that's based on 3D printing. And you'll see that we've now incorporated an almost recognizable joint structure into these hands with the goal of being able to control the low stiffness and higher stiffness directions of motion a little bit better. And if you've been watching this video in the lower right, this is footage from our lab from just a few days ago. So one of my students, Pragna, has been working with our latest model, which she developed in order to pick cards off a stack. And at some point, she just started to pick them all up and put them back on, just kind of as a free form experimenting with the hand itself. So I think this example highlights some of the things that are hard. So it both shows some interesting capabilities because the hand is very dexterous, but at the same time, this very intentional fine control of dexterous manipulation is still, I think, more difficult than it needs to be. And we would love to be able to address this difficulty. And partly, I think that's going to be solved through development and introduction of new materials. With that, I'll hand it back to you.
All right, thanks, Nancy. No, really cool to see kind of the iterations on these designs and how they've been evolving over the years. So, really awesome stuff. All right, so Jan, I mean, your work covers quite a spectrum. I mean, you've done, everything from soft robotic systems, grasping manipulation, to really understanding the underlying sensory and motor functions of the natural human hand. So what are some of the architectures that you've been exploring, and how important is it that you replicate some of the characteristics of actual natural hand function?
Sure. And hey, thanks to everybody for putting together this this great session. Let me go ahead and share a video that illustrates a few things. So yeah, we conduct research on broadly on haptics, robotics, and some emerging technologies motivated by challenges in each of these areas. Haptics is a core topic of our research. We'll work on kind of both fundamental science and engineering design research, as you said. Haptics, to me, refers to our capacities for touching, feeling, and manipulating objects in our surroundings. So research over several decades shows that in humans and in other animals, touch sensation and motor control are inseparable. In this sense, haptics is central to our abilities, or even synonymous with our abilities to physically interact with our environment. One major thread of research in my lab is on understanding how human haptic abilities, or haptic abilities of the human hand, are supported by biomechanics. So we study a few different aspects of this: interfacial contact, which is important for perception of features of surfaces, their properties, or for manipulating or grasping objects. Actually, more recently, we've done quite a bit of work that regards on understanding how sensation and perception are supported by the biomechanics of the hand. And in particular, some of our work demonstrates that there's a sense in which biomechanical coupling of soft tissues in the hand implements perceptual processing prior to involvement of the nervous system. We also work on soft robotic and electronic technologies, some of them informed by human abilities, some of them informed by other biological systems, some of them rather different. The example here shown on the right is a robotic gripper that we reported a few years ago that uses a few different principles, one of which is envelopment. So similar to a few other soft robotic gripping designs or some biological systems, it sort of encloses objects and does so with a really simple mode of control input with a single fluidic port. Nonetheless, we've designed the soft mechanics of this structure, the composition of this thing, and the interfacial adhesion, which is enhanced through the use of a kind of gecko-like skin in order to allow it to grasp a lot of things. We've worked at different scales. There's a kind of miniature, very fast gripping device there shown at the bottom. So yeah, I found this kind of intersection of topics to be really exciting, but there remains the question, like you said, of whether much the attention that we give to the human hand as a model for a generalized gripper is appropriate, or whether that reflects some kind of perhaps anthropomorphic bias on our part.
Right. Yeah, and right, and I mean, I think these videos actually, as with a lot of these intros, I mean, we're getting this sense also that there's just a lot of different roles of materials and just kind of different form factors and overall architectures. I mean, you just showed that kind of that vacuum type, enveloping or kind of collapsing gripper. I mean, Elliot, you showed the gecko inspired right grippers, and Tess, I mean, you were kind of looking more on the sensing side, right? So we're kind of seeing all these different applications of materials. But I guess maybe a kind of just to start things off with kind of just broadening out this discussion a bit is why new materials? I mean, we know that in industrial automation and kind of robotics more generally, I mean, parallel plate, grippers, suction cups, jaws, I mean, those are, ubiquitous, right? I mean, incredibly popular. So what kind of new ideas are we really bringing, when we start re-examining the types of materials that are being used? And I just want to kind of, just real quick, I mean, when I talk new materials, I mean, either we could talk about kind of utilizing existing materials in new ways, right? I mean, so Nancy, you were showing like the use of foam, right, in your grippers, or are we talking actually generally introducing new types of material systems like the gecko adhesive, like that reskin, that kind of pressure sensitive magnetic skin. So maybe Elliot, I'll kind of start with you. I mean, having worked with all these different architectures, I mean, when are these new materials and gripper designs truly useful?
Yeah, no, I think it's a great question. And I think actually you might have kind of led towards what I was thinking with setting kind of a baseline with these very simple parallel jaw grippers and suction things like this. I think if we're creating new fancy complex grippers with brand new materials and they don't outperform what you can do with a pinch gripper, then I'd say that's not a useful case. That's a situation where you're not adding. But if we can kind of keep that as a baseline and say, okay, well, if that's kind of where the level we need to exceed is, then if you're adding some new capability that's beyond what we can see with traditional grippers, then those are maybe the use cases where it's going to be more viable. And those might be more in the cases outside, repetitive manufacturing tasks. If you're doing something very precise, repeated over and over, exactly the shape of the piece in your manufacturing line, we have pretty good solutions for that. And that's maybe not where we really need to innovate. But as we move outside of these situations and we want grippers to be working like a human hand can, and basically, work with all kinds of different materials and applications, object sizes. I think it's in those applications where we're going to need to see some innovation in the new materials areas.
Right. So, and also kind of taking a step back. Also, I mean, when we kind of think about grasping, I mean, there's kind of the gripping, right? And then there's also the manipulation. And kind of Nancy, I mean, in your videos, you're kind of showing like, ability to kind of pick up playing cards, but also doing kind of in-hand, manipulation. And I'm just kind of curious if, from your perspective, if the materials challenges or the conversation around materials is it different depending on, whether we're talking about grasping or manipulation?
I think that it is. So first of all, I want to say, Jan, I really love your grasping robot. It looks so much like a sea creature to me, and I feel so happy every time I see it. So very cool. I think Elliot was involved in that too. So I enjoy that a lot. But I think once you get to doing something very dexterous, there's some things about the problem that do change. So one of the things that we notice a lot is we have to start paying attention to our gripping surface very carefully. So there are certain times when we want it to be very sticky and certain times when we want to be able to slide across the surface. And the human fingertip is so good at that, right? We're able to hold on to objects tightly and we're able to slide across surfaces in order to adjust our grip. And we find ourselves, being very careful about the materials that we pick in order to do that. I'd love to be able to adjust that on the fly, and certainly there have been some solutions out there that have been offered for that. Another thing that changes, I think, is how the system reconfigures itself. So it has to reconfigure itself actively in order to change the configuration of an object or perform a task. If you're using a tool or doing a twisting or dynamic pushing motion. Like there's this, one of my students was looking at just the simple thing of picking objects off the table. Think of picking your cell phone off the table. It's something we do all the time. And people make lots of mistakes when they do things like this. And we have this bicycling motion, she called it, that we use, where we just kind of pedal our fingers until we're able to get some friction purchase on the object and pry it up off the surface. So being able to do these kinds of reconfigurations. Now, we don't have to use fingers, but we have to have that dexterity, those degrees of freedom in the system in order to be able to accomplish these kinds of motions. So those things come to mind. And I think that as we start to manipulate things within the hand, also local shape changes matter. So the shape of the palm matters, the shape of the fingers start to matter. So Elliot keeps doing this pen twirling thing, which is very compelling to watch. And I think that the success of that depends on, what is the shape of the fingers like. So my student, we just saw picking cards off the table, found that she did a whole like 600 different experiments with different robots and tasks, and found that she did 3 versions of this hand and found that she overshot with the fingertip design. She thought, oh, it's too round, I can't do these things, I need a flat surface. Then she went too flat and found, oh, well, I actually need a round surface. And our finger does both, right? We have flat parts to it and round parts to it. And this kind of practical experience, we need to build it up either through simulations or trying things out. And so all those things come into play. It's a little bit maybe too long-winded, but
no,
I have a lot of opinions on the topic.
No, I mean, there's a lot of great points there, right? I mean, the geometry, the reconfigurability, the compliance, and I mean, this is what kind of enables a lot of these kind of material systems to kind of embody a lot of the functionality they need for these tasks. I guess I'm also kind of the other big factor is of course the sensing, right? And Tess, this kind of ties into kind of what you were saying in the introductory remarks, right? I mean, what is your perspective? I mean, is sensing needed, for these types of tasks? And to what extent are kind of the existing sensors, tactile skins that are currently used in robotics, are they good enough, or is this still an area where we need better materials?
Well, starting out by putting aside my researcher bias, my answer is no. We need way better sensors. And I think coming from the research perspective, we just don't understand the problem at all, really. Like, we don't understand what forces are applied, where and when, how that whole grasping policy plays out over time. And we don't understand how we do it as humans, although we have a pretty good understanding of the physiological sensors at play in our skin. But if I make an analogy, when a designer is picking out a motor for their project, they understand the amount of current it needs, the compatible motor driver, and the applied torque that they'll get. I think that's what we need for touch sensing. So I want a robot that works in a structured environment and picks up this many kilos. There should be a very set design spec for those. And I think a lot of people in this group, we're thinking much larger. We're thinking, what are the design specs we need to get an unstructured environment, soft hand that can handle mistakes and do dexterous in-hand manipulation? And I think that's where a lot of the interesting questions start to come up, where we don't really have answers for most of them.
Right. Yeah. Yeah. I mean, yeah, having those specifications, I mean, yeah, it's certainly very important. But I guess what I'm trying to get at maybe is maybe a layer actually above that, right? Which is, is sensing kind of even needed? I'm just thinking about, I mean, if you have an anesthetized human hand, right? I mean, yes, motor tasks become much more difficult, but a person can still, has some, capability of perception. They can still oftentimes complete the task. I mean, Jan, I mean, I know you've kind of looked at the sensory motor functions of kind of natural hands. I mean, how important is kind of tactile sensing kind of, in that respect?
Yeah, I mean, while it's true that, and I don't know if everybody in the audience is familiar with this idea, but it's true that local anesthesia applied to our fingertips will prevent humans from performing will greatly, like dramatically degrade the dexterity of grasping. So picking up a pen, writing your name, and things like that become arduous tasks. And while it's true that one can still, if the motor system is intact, one can move and interact in some coarse fashion. These sorts of interventions are severely, debilitating. There are, a number of diseases that result in peripheral neuropathy, leading to loss of sensation, type 2 diabetes, chemotherapy, quite a few other conditions, stroke, and in rare cases, there are examples of people with congenital disorders that have led to whole body kind of touch sensory loss. And in practice, what one finds is that people affected by such disorders elect not really to physically interact with the world. I think, getting a little bit more granular, it's helpful to think about, and can be challenged to introspect about it, but it's helpful to think about tasks like, grasping a pen, identifying the correct grip location. Well, there's sort of like small object features that are really critical to, finger placement and to our ability to manipulate such things, manipulating small objects, lifting a coin off of a desk. These things require, at a sensory level, that we collect information about the contact conditions with those with surface features, about the forces that are supplied, or even like gross movements like grasping. If you're grasping, humans grasping objects will supply grip forces automatically that are just a little bit higher than the minimum necessary to move things around. Anesthetize a hand, we over grasp. It becomes very inefficient. So the same thing can be said about touch perception. If you degrade kind of our ability to move, that's eliminated as well. I think I guess to me it's a little bit challenging to discuss requirements outside of some overarching goal. Is the goal implicitly to realize, so robots were originally envisioned as sort of human-like automata, right? And so from that standpoint, if we wanted to realize that vision, perhaps it's true we'd like to approximate as well as possible humans' abilities to physically interact with the world, and that that probably demands that we think carefully about the mechanics involved, the sensory channels, and the control, and all sorts of other things. On the other hand, there might be other goals here, and I'm curious as to others' thoughts about this. Is what would represent transformative advance in grasping and manipulation technologies and robotics generally? What are we looking for, and what is the optimal solution to that? Something that might look like a human hand, or might it look like something very different? I don't know.
Right. Yeah, I mean, that almost speaks to kind of, the need for like a universal type of gripper and effector that can kind of do, a wide range of tasks. But I mean, your other point, does echo Tess what you were saying? I mean, a lot of it also is specialized, right? And for certain use cases, certain applications, as engineers, as a designer, you do want to know what are the available sensors, what are their specs, and is it right for your particular use case? So I mean, one use case is Nancy. I mean, what you've been showing, right, with your phone grippers, and they have this tremendous capability to do in-hand manipulation, and they don't have any sensors at all, correct? So do you not have sensors because you don't need them, or?
So our philosophy so far has been to just see how far we can get with no sensors. And I believe that we're not even close to where we can go with that philosophy. So one thought about this that I can talk about is that if we think about how people hold objects, grasp objects, a lot of the grasps that we have are fairly low energy. They feel comfortable to us, right? And that is not necessarily the case for many robotic grasps. They're not necessarily low energy. And if we imagine that we can, and we designed a little widget to test out this idea. So imagine holding a credit card with a pinch grasp and holding a credit card with a key pinch, right? They're a little bit different grasps. So we built a little widget and it would comfortably hold in this pinch grasp, it would comfortably hold in a key pinch. A little bit of energy would kind of kick it from one to the other. So I think that we can push that kind of idea to a, kind of a broader range of in-hand manipulations where we're comfortably holding objects in standard grasps with relatively little energy, making use of the passive mechanics of the system, and then kind of kick them into other states with a little bit of input of energy. This sort of idea has been sort of tried out, but not quite this way with the prosthetics that are active open. But I'm thinking about something where we try to understand the families of grasp, the space of possible grasps and manipulations in a much more energy focused way. And so I think that's just one example of what we can do. Another example of what we can do without sensing is we can make much better use of joint limits. So our own hand, the human hand, has both of these features built into it. We use joint limits all the time to transfer forces up to the stronger muscles in the skeleton, and in order and the passive dynamics of our system to help us avoid damage when we collide with objects, which we do all the time. If we watch people in slow motion, they're making all kinds of mistakes. And so I really want to push the limits of this and just see how far can we get? How much easier can we make it for my student with the VR equipment there to do things with all, just her, vision as feedback. So that's my philosophy on it, but full disclosure, we are working on sensors. So, there's a little bit of both there. And I agree with what Tess said too, that there's a lot we don't know. So we're really pursuing measuring where people make contact with objects in everyday life, because I think that's so important. Where do they make contact? And if we're going to design robots, one of the issues that we've had with rigid robots has been the contact areas are so tiny, it makes it hard to create robust grasps. And we need to move away from that. And we are moving away from that with the soft robots. And that's been really exciting. But I feel that we don't quite understand where those contact areas are, how they're used, how they change. And that doesn't have necessarily to do with sensing, but it feeds into the design process.
I mean, as academic researchers, we have the luxury sometimes of just being dogmatic and seeing how far we can push a particular design approach. But, Tess, you do bring up a good point. In practice, in reality, yes, we have to kind of have kind of an all the above type approach. So I do want to kind of move on. I don't know, Elliot, if you had anything you wanted to add before we move on to the next topic.
Yeah, I think we can keep going.
Sure. So, and Elliot, actually, I kind of, for this next topic, I was, had specifically your kind of gecko adhesive gripper in mind here, right? Because, we know that, when we, work with these kind of soft materials, I mean, there's all these like new functionalities, but especially within this domain of kind of soft robots and soft robotic grippers, there's all limitations, with using soft materials and fluids, right? And, questions about, how good they are with lifting heavy objects, bulky objects. So I was kind of curious, Elliot, just to get your perspective on, what are some of maybe the downsides or challenges with working with soft materials in this context? Yeah,
absolutely. So if you think of a gripper essentially as a spring that you're controlling the displacement of it, onto an object. If your spring is very soft and you have some limited displacement, then your force is going to be limited. And if you're using friction, then from my previous plot, if you remember, there was basically a line relating your squeezing force and your frictional force. So it means if you're picking something up and you can't squeeze very hard, then you can't apply very much force, right? So if I very gently squeeze it, it's pretty easy to pull it out of my grasp. So I think that's a fundamental limit with soft grippers in our lab and your lab. A lot of labs have looked at these, silicone grippers, and while they're useful for picking up strawberries and very gentle light things, fragile light things, I think a challenge with them is if it's really going to be a ubiquitous gripper, well then you're helping out at home, for instance, you need to pour a gallon of milk, is that really going to be able to do it? And so I think, there's been quite a bit of work on variable stiffness, and I think that's a really cool area to examine. The gecko adhesive is an interesting material in that it can apply those large forces without a large squeezing. So we are able to pick up very heavy objects kind of in a pure, if you're lifting in this direction. Manipulation is still obviously a challenge if you have a soft gripper and you're trying to spin it in your grasp. You are going to need something that's stronger and stiffer at some point if you're going to manipulate and not just kind of lift it up by a string. But yeah, so I think being careful with our, when we are designing these new grippers and looking at the compliance and thinking about, well, maybe there's niche areas where those are very helpful, and if you are going to try to make something more universal, being aware that you might need to change stiffness to be able to adapt to a range of tasks.
Right. Yeah, that makes a lot of sense. So I mean, a lot of really kind of interesting kind of points have kind of brought up, and I mean, there's quite a number of directions I could kind of see this conversation go. However, I did want to kind of pause for a moment and take a look at the Q&A, just because we have gotten a lot of good questions from the audience, and so I might actually pitch this out just to the whole panel. So first question here is evaluation metrics. So, how do we know the impact, and then how do we kind of quantify or measure the impact that new materials are having kind of in grasping, or how will we do that? So I don't know if anybody wants to jump in here. I mean, Tess, you kind of alluded to this a little bit, so I don't know if you want to start.
I mean, I can jump in and say that I think this is an ongoing problem. It's like hardware, and right now I consider all these grippers like artisanal, grad student made, and one of a kind, and it's like very difficult to set them up to be compared. I think we can take some lessons from some other fields like computer vision, which has like a set of benchmarks. So maybe, as a community coming together and deciding like we are going to add one force sensitivity metric, one force resolution metric, and do our best to match each other. I don't think it'll be perfect, but it's a start. But I do want to avoid assuming that like every lab has to build a very similar robot setup. I just don't think that's going to move everyone forward at the speed and direction that they want. But yeah, I think, community building some sort of benchmark that's accessible would be my first start there.
Right. Other thoughts?
It seems like a challenging question. To me, it does connect back to some of the other comments that were made. I mean, as Elliot said, in conventional sort of automated manufacturing, existing gripper designs, rightly work quite well. We have plenty of really talented engineering designers there. So perhaps another, I agree that having benchmark tasks could be really valuable, like the Amazon grasping challenge sort of thing. Maybe something a little, I don't know what that would look like in a way that's sort of broadly representative. Maybe another way to think about the question that occurs, that comes to mind would be to think in terms of, emerging areas of manufacturing or industry or field, operations. So agile manufacturing, is that what would be a design that could be implemented for, in a way that could allow manufacturing lines to be repurposed or rapidly, adapted to a variety of, to exploit a variety of opportunities that require much more investment today. It's an intriguing question, because I think as researchers, we tend to, focus on, we have some system we're working with, and we tend to analyze sort of what's it good at, and that's sort of what we'd like to highlight. If I put on my designer hat, I'd rather have a clearly delineated problem. to solve a set of objects or something like that. And I feel like this question of like benchmarks fits somewhere in between those in a way that's requires someone smarter than myself to analyze.
I mean, I'm thinking. I mean, one. I mean, yeah, certainly. I mean, there's kind of a lot that could be explored there. I mean, one maybe top line, way of thinking about like impact and metrics is just from an economic standpoint, right? I mean, we know that there have been examples of startup companies, university spinoffs that have had success with commercializing some of these soft robot grippers or utilization of new materials in gripping. I mean, I'm thinking companies like Empire Robotics or Soft Robotics Inc., where there's been billions of pick and place operations I know that have been performed using their end effectors. So I don't know, maybe from that commercialization and entrepreneurial standpoint, I don't know, Elliot, Tess, I mean, you've kind of had experiences or at least connections kind of with that side of things. I don't know if you have any perspective you want to share there.
Yeah, I can go ahead just briefly. I have a colleague who works at a robotics company making arms mostly, but he's in charge of the grippers. And something he's been interested in is some of the gecko adhesive stuff. There have been a few gecko adhesive grippers commercialized, and the adoption has been relatively slow. And from his experience, his customers tend to be on the conservative side. If you tell them, I have this new technology that might work slightly better than your current technology, or you can just, I can give you a parallel jaw gripper, they're going to say parallel jaw gripper every time. So I think this is something to keep in mind as we're kind of looking at how well these new technologies do on the market, especially for manufacturing applications. It could be a little slow. Adoption could be a little bit slow, and so this might be something that's going to take a little bit longer until technologies are more proven out before they're actually ever going to be adopted, if they're ever adopted. What occurs to me also is that a different way to me to think about this is perhaps other advances in robotics would be needed in order to really exploit. Like if we could create today a dexterous, like something that closely emulates capabilities of the human hand across different areas. I'm not sure that we have the infrastructure right now to exploit that. And in addition, it's sort of like having something of that nature, similar to the advent of the computer or of like video displays. It's going to transform the opportunities that people explore, and so maybe I think there's reason to be a little bit resistant to the idea of trying to address this question of like how will it be used today. 30 years ago, it was not widely believed that people needed what was at the time, tantamount to a supercomputer in your pocket with a big screen on it. And if you come up with a list of potential applications for such things at that time, it would probably be rather different than the wild world of mobile computing today. But yeah, just a thought.
Yeah, and just adding a short note to Jan and Elliot there. I haven't worked in any startups, disclaimer, but the takeaway I read about the community is you have to be a lot better solving a big problem for a targeted audience. And that is already hard for any startup. And soft robotics startup has to do this with almost no existing infrastructure for building that technology. So I think it's a really big challenge, and I look forward to seeing what's coming up in the next 5-10 years.
Yeah, and I'm sure, and that's going to be led by a lot of folks in the audience here. So yeah, I'd share Tess's enthusiasm. Here's another question that came up from the audience. This is about issues of wear and damage, right? So, Elliot, you were talking about, the load-bearing capacities of, some of the softer materials that are used with these grippers. And so kind of another challenge or maybe even shortcoming of these materials are their wear properties or susceptibility to damage. So, Nancy, I mean, you've kind of, experimented a lot with different types of foams and also different types of fabrics, textiles, as you've worked through these different iterations. So I don't know, is this a problem that you've come across?
I guess I can start and then maybe pass it along to Elliot. So the very first robot that I showed, the one that looked very human-like, and in fact was made from a Hollywood life casting techniques. That one, it traveled around for 2 years in people's suitcases and went to various conferences and did a lot of demos and went through tens of thousands of repetitions and still worked fine. So in terms of robust, I would say that shows a certain level of robustness that we were pretty happy to see. And I think, I think we've been overall very pleased with we started out designing these hands thinking, oh, it doesn't matter if they last a long time because we can just make a new one, mold a new one, and we can print a new one. And then we found that they ended up lasting for years. So I think that their robustness is maybe surprisingly good. But then of course there's the other side of it that you can just make a new one and it's not very expensive and so on either. So that's my take on it. Yeah, we found that the failure modes were things like, how we attach the glove to the foam, things like that, like simple things like that we had to come up with solutions to over time, rather than the body of the robot itself or the actuation system itself.
Yeah, I'll just address the, maybe more on the interfacial level, these microstructures and things like this. Interestingly, so some microstructures are almost a tacky material, so like a urethane, and those do not last so well, and they tend to tear or get very dirty. I think that's another challenge with any kind of adhesive type system. The gecko is this amazing material, the actual gecko, where it's actually very hard materials like this, your fingernails, and so it doesn't really get dirty at all. It's self-cleaning. So that's an interesting, I think, a goal that we still have in the field of gecko-inspired adhesives to reach to that kind of level. And then also they can mold and regrow their adhesive as well. So that's another cool feature we're still working on.
Yeah, regenerative. So, I mean, we've talked about kind of, why new materials, right? But I think a lot of you have made a kind of compelling, case for, with manipulation, with sensing, actuation. I mean, there is this kind of case for why we would need new materials. I guess to kind of maybe flip the question around is how best to accommodate these, right? I mean, especially from the perspective of AI. Or the existing, control methods, AI tools, data-driven techniques, are they sufficient for a lot of these new material systems, or is there still kind of more work that we have to do on that side? Maybe Tess, I know this is kind of pretty central to the research that you do, so maybe you can start.
Yeah, maybe surprisingly, I would say I think there's actually huge value in continuing like traditional control theory options. I think it's a great starting point, and the reason is, for robotics and tactile sensing, you'll never get that scale of data you need to build this like perfect generalizable model. Like, we aren't ImageNet. We're not going to have billions of YouTube videos at our disposal, I think. And I don't know if we should try. We should like manage our resources a little better. So I kind of view the long-term solution being a hybrid, like a core closed form control theory solution with a fine-tuned data-driven method on top, something like that.
Others have thoughts on this?
Well, I think it's come up parenthetically here and there, but I think one of the attractive features of many soft material designs is that they offer more compliance. They can conform to surfaces in ways that or produce larger contacts, and so control becomes easier. With fingered grippers, there are some significant challenges if it's depending on the sort of diversity of grasping tasks involved, can controlling, individually actuated digits to achieve some grasping task. It's demanding, and so, but if depending on sort of what's needed, I guess the motivation for something more hand-like becomes stronger once we start talking about manipulation and things like that. But I think in any event, this interplay between sort of morphology, mechanics, and control is interesting, and I think an area that soft robotic designs can offer really systematic advantages.
Right. Yeah. Having that.
I would like to, if I may, just throw in a couple of things. I would like to see beyond just sort of the typical, oh, we're going to control the joint angles of our mechanism or the tendon tensions. I would like to see controllable softness and controllable stiffness and things like that as well, which I think are we can do now, right? Because we have this ability to design materials that have these properties.
All right, so I think we're actually going to end it there. We're pretty close to time. I know that Kevin has a few closing remarks to wrap things up. So I want to thank all the panelists. This is a really fun conversation. A lot of questions and topics we didn't get to. So hopefully we'll have a chance, in the near future to kind of continue this. But for now, we'll just kind of stop there. And Kevin, I'll turn it to you.
Thanks, Carmel and Elliot, Tess, Nancy, and Jan for that fascinating discussion. And of course, to you, the audience, for your active engagement. We had lots of questions, many we couldn't get to, and I apologize for that. Clearly, this is a rapidly growing, exciting field. As editor-in-chief of the Transactions in Robotics, I see more and more papers in soft robotics, new materials, tactile sensing, and there's a lot more that we still need to learn, but I think today's session touched on a number of topics that are of great fascination right now. I'd appreciate it if people who attended could fill out the survey that will be sent to you shortly. And I'd also like to remind you that we have another webinar coming up. Another webinar coming up on March 2nd, being run by Julie Shaw on the economic and societal impacts of the coming dexterity revolution. So I'm sure that will be fascinating too. So please join us on March 1. And March 2. And thank you again for joining us today, and have a wonderful week.